Okay, so thank you everyone, and welcome to this wonderful talk. Actually, very excited. This is one of the first talks from the Center of Excellence for Quantum Computing, Information Science and Technology. And so our speaker today is Professor Florian Marquardt, who's very well known to those of us who are in quantum optics and quantum information and associated areas. So let me briefly introduce him. Professor Marquardt did his PhD from the University of Basel in 2002 in the group of Professor Christoph Bruder. And then he did postdoctoral fellowships at NCCR Basel and at Yale. And then he joined LMU as a junior research group leader, and then moved to Erlangen Nuremberg as a full professor. And now he's the scientific director at the Max Planck Institute for the Science of Light in Erlangen. So an eminent speaker that we are very delighted to hear from. He's the recipient of various awards, Emmy Noether Group Leader Fellowship, and the Walter Schottky Prize of the German Physical Society, to name a few. So he's going to talk to us today about, I think, an intersection of two very exciting fields for many of us on campus, machine learning and quantum technologies. So I invite you to hear this talk. I just want to make one administrative note that there are some snacks and chai, the usual local affair after the talk, so please stay back, enjoy, and also you can interact with Professor Marquardt. So please take it away here.
I'm happy to see so many of you here. It's my first time to India. I arrived on Sunday. I already had many great interactions also here this morning with my colleagues here at the IIT. So my talk will be about, indeed, the intersection between machine learning and quantum technologies. That's something we went into in 2016, 2017, when we asked ourselves all these great new neural network techniques that were being introduced by the computer scientists, what can they help us in terms of, for example, building better quantum computers? So that's what this talk will be about. Now, I want to start on a very general level. Think of your brain. There are many ways to think of your brain, but a very simplistic view of the brain might be as an information processing machine. So you receive some input like sound or images, then your brain processes this input and it finally produces some output, for example, a word that you say or an action that you take. Now, the amazing part about this information processing machine is it's very flexible, it's very robust. In fact, if you see a picture of a light bulb that you've never seen before in this particular shape or from this particular angle, then instantly your brain will still recognize it as a light bulb. And from the point of view of a programmer, this is amazing, because if you wanted to hard code an algorithm in software that did the same thing, it's basically impossible. So the idea came up that one should look into how the brain does this and maybe build something like an artificial brain. So if you look inside the brain, it consists of neurons, which are simply biological cells, but they are connected by this very dense network of connections, and electrical pulses are traveling between one neuron and the next. So this is a realization that was realized already 100 years ago, and then people understood the electrical pulses and so on. And so since about half a century or even more, people have had the idea to build something similar, but now on electronic computers. And one would name those things artificial neural networks. Now, very briefly, an artificial neural network also consists of neurons. These are the circles in this picture. But in contrast to biological neurons, these are much, much simpler. In fact, at any given moment in time, any of these neurons only carries a single number. The bigger the number, the stronger the activation of that neuron. So that's all the properties of any single neuron. Similar to the brain, these neurons are connected. And also similar to the brain, the strength of these connections is variable and can actually change. The overall idea of the structure of such a neural network would be that you feed in the input as a string of numbers into the lowest lying layer of neurons, and then by a series of rather simple calculational steps, layer by layer, you go to the output layer and calculate what should be the output of the neural network for this particular input. And then it's your job to interpret this output, for example, to say, if the neuron on the right has the higher value, then that might mean that the input represents the image of a dog. If it's the neuron on the left, it would be the image of a cat. And the idea would then be to achieve the same as your brain can do, namely to recognize, again, a light bulb in an image that has never been seen before. And the way this is done is by adjusting all these connection weights in just the right manner. And instead of you adjusting the connection weights, in fact, you just use millions of training examples of images together with the correct label, and you try to adjust the connections such that you come closer and closer to the correct input to output mapping that is prescribed by these training examples. So you don't need to hard code anything. No one needs to write an algorithm that works for these particular images. It's all in changing these connection strengths and coming gradually, slowly closer to the correct input-output relation. Okay, so this is artificial neural networks. Now this has been around for more than half a century, this idea, and there were ups and downs. But the real breakthrough came in 2012. And that is the first time that a neural network was able to beat all other approaches in one of those important competitions that computer scientists organize. In this case, you're given 1 million training pictures, all annotated by humans. They have already the correct labels. You can do whatever you want with them using your algorithm, in this case, train a neural network. And then afterwards, you will be tested on pictures that you haven't seen before. And their neural networks were able to beat all the competition. And since then, they are also beating humans. Now, if you are interested in the basics of this, in principle, there are many good lecture courses on the internet. I myself have given a lecture course that is geared toward physicists, so using the knowledge that you should have gained in the first 1 or 2 years. And there's both a basic lecture course here and an advanced machine learning course, more on the conceptual, more mathematical stuff. So I invite you to also have a look at these lectures. So before I come to the main topic of the talk, I want just to briefly mention what our group does in this domain. So machine learning applied to physics is our main focus now. For example, we apply machine learning to photonic structures, photonic crystals as an example, to optimize those structures very efficiently. We look into the general area of what you might call artificial scientific discovery, where the goal is to build an artificial scientist, so to speak, a computer that can come up with a hypothesis, test it in the most economical way, and then move on to analyze it and come up with the next hypothesis. We are also turning things around in the sense that not only what can machine learning do for physics, but we're asking what can physics do for machine learning. So this goes under the heading of neuromorphic computing. And there, for example, we're looking into how can nonlinear optical networks be made to learn in order to function in a way similar to artificial neural networks. But in this talk, I want to focus on, as I said before, applying classical machine learning, so the artificial neural networks that come from computer science, applying these to quantum technology. And so here's the setting. You have your quantum computing chip. You want to design, for example, very smart sequences of quantum operations. And you're trying to do this with the help of an artificial neural network. So what can be done if you set yourself this goal? And if you're interested in having a bigger overview that I can deliver in this talk, then I also invite you to read this review of ours that we recently put out as a perspectives article in Physical Review A, where we cover the whole field of classical machine learning for quantum technology. So, among all the different machine learning techniques that exist, the particular set of techniques that I will be focusing on here is called reinforcement learning. And so let me tell you what this is about. If I'm only allowed to use 2 words, it's about discovering strategies. Finding out good strategies, for example, to control your quantum computer. And in order to understand the context, I want to point out that about 90% of applications of neural networks are rather from a different domain, namely so-called supervised learning. So supervised learning is what I introduced to you so far. That means you have a large set of training examples and you are always being told the correct labels, the correct answers. It's really like having a smart teacher teaching a student by way of example, many question-answer pairs, and eventually the student might get as smart as the teacher and maybe even extrapolate a little bit from that knowledge. However, the final level of this is obviously limited. And so the question is, if you want to be a really smart student, becoming better than your teacher, or if you want to be a researcher discovering new stuff, how would you go about this? And so that's the domain of reinforcement learning. Because the only way we know how to go about this is to start with some completely random trial and error, and then to notice what works and what doesn't. And if something works even only a little bit, then maybe you try to repeat it and modify it slightly in order to come to something that is even better. So on a general level, it's like an optimization problem, but you really start out as random. And this is called reinforcement learning. It's called reinforcement learning because in the end, you're trying to reinforce the parts that work, the good actions you want to reinforce. Famously, reinforcement learning was used to solve a very challenging question, namely, can you teach a computer to beat the best human players in the game of Go? And this was achieved a few years back. And that certainly was also an inspiration for our work in this domain using this technique. So if you'd ask a computer scientist, how does reinforcement learning work? There's always this kind of picture. You divide everything into two pieces, namely the environment and the agent. The environment is really the world around you, which you can manipulate and observe. The agent is like a little robot or a neural network whose task it is to achieve some goal inside this environment. And it can achieve this goal by taking in observations of what it sees and trying to suggest actions based on these observations. So suggesting the proper action given the incoming observation, that's called a policy, or you could call it a strategy. And then you apply the action. The action will affect changes in the environment. Then you make the next observation and so on. So you go through this cycle many times. It's like having a trajectory in time, action, observation, action, observation. And then at the final time, let's say you do this for 20 time steps, you get a reward based on the task that you're supposed to successfully perform. So for example, you want to stack these blocks, then the reward will be how many blocks you were able to stack. And the overall goal of reinforcement learning is to, over time, over many trial and error runs, improve this reward, because that means you have become good at this particular task. And it's our job as users of this technique to define the task and to engineer a reward that encodes the task that we wanted to solve. Okay, so this is reinforcement learning. Now there's an important distinction here that will become important later. If you look at the world, the environment around you, it could be that you do have a model of this world with equations that you can simulate, or maybe you don't have a model, and both are interesting scenarios. So if you don't have a model, you will treat the environment like a black box. And this is often useful. For example, the environment is really a quantum device inside a dilution refrigerator and you don't know exactly its parameters, so maybe you want to use this approach. And the other approach would be if you say, I have a very well-characterized device that I know very well and I know the equations of motion, then that would lead you to so-called model-based reinforcement learning. And I'll be talking about both of those. But let's first stick with model-free. Now, to give you a little glimpse of how this works behind the scenes, that's what this slide is for. One way of doing this model-free reinforcement learning is to say, given the observed state S, what is the action I should take? And a smart way of encoding this problem is not to say that this is a deterministic mapping, but that you have a probability distribution. Given the state, there's a probability distribution of the different actions that you suggest, and some probabilities are larger than others. And then the trick will be that during learning, during training, you will change this policy, this probability distribution. That's why it carries here this parameter theta, so it can change. And then what you do, surprisingly, is very, very naive, and it's very surprising that it works. You do gradient ascent in the reward. So at the end of each trajectory, you get a reward. You average over many trajectories. This reward does depend, of course, on the parameters of your policy, because if you take a different policy, you get a different reward. And so now you can take gradient ascent. So you change in little steps the parameters of the policy going in the direction of maximum change of the reward. And if you work it out, there's a little bit of math behind it. You have these derivatives of the logarithmic policy probabilities. So it's really a very old algorithm. It's, so to speak, a grandfather of a whole family of algorithms by now. And it's very surprising that it works. Yeah. Good. So let me first tell you a story that is already a little bit older, a few years back, which is the first work that we did in this whole area, and where we really introduced deep reinforcement learning to the field of quantum physics or to the field of quantum computation. So what we asked ourselves at the time was, what might be a good application case for deep reinforcement learning in physics or in quantum physics? And you want to pick a situation which is close to feedback, because you saw this observation-action loop that is really feedback. So among the many applications of feedback, you want to pick an application that is a little bit more complex, and one complex application of feedback is quantum error correction, where the idea is you prepare a qubit system in some rather complex state, and then you take some suitable measurements in order to check whether the state is still alive or whether you should correct it in some way. And so the example we pick is, we imagine there's a small module consisting of several qubits, and they are subject to noise. And your goal is simply to protect the quantum information that is stored inside these qubits against the noise. We know in principle that this is possible, starting from the work in the 90s by Peter Shor, for example, on quantum error correction, and also many other smart ideas in this direction. But can a computer discover such strategies for a particular noise model, for a particular connectivity of the qubits, for a particular set of gates? Can it discover this without knowing anything about these techniques? And so here's again the same graph. We have the qubits with the noise, and then we can take measurements. These measurements will be fed into a neural network, and the task of the network is to suggest the next action in terms of these probabilities for different actions. So now I want to define in some more detail the game that we are playing, because every reinforcement learning application is like a little game that you want to win. So what we say in this particular case is, you initialize one of these physical qubits in a superposition state. It's an arbitrary superposition state, and your goal will be to keep this superposition alive. But you don't know which superposition, so it's really a quantum error correction task, not just a stabilization task for a given known state. It's an unknown state that you want to keep alive. What can you do to do this? Well, you have all these other qubits available. You can apply gates to the qubits. You can maybe also measure from time to time. So in order to show a possible strategy, I plot a quantum circuit. Time runs to the right. Each line corresponds to one of the qubits. And you might just start, say, by applying a controlled NOT operation between two of these qubits, flipping the second one depending on the state of the first one. Now you can go on, and if you don't know anything, you will do random stuff like this. Eventually, maybe you decide to measure one of the qubits. So let's measure the qubit. Now, it turns out, if you follow this closely, that was a very bad decision. Because by doing these controlled knots, you have entangled all the qubits, and now by measuring only a single qubit, you will suddenly collapse the whole superposition. So instead of preserving the quantum information, you collapsed it. But you should realize that at the beginning of the game, the agent is in exactly this situation. It doesn't know what it's doing random stuff. Most of the time it will collapse the superposition. But if you then apply these reinforcement learning algorithms, gradually it will learn how to do things in a better way. And so I'm showing here typical sequences of gates that it applies during different stages of the training. So this is very early on. It does some random stuff, and then suddenly the quantum information collapses. That is indicated here by this blue shaded area. And afterwards, it doesn't even matter what it does anymore. But afterwards, it discovers to do things in a better way. For example, it avoids these very catastrophic measurements. It then finds that it can do multiple controlled NOT operations in order to entangle these qubits, and it finds what we recognize would be the so-called repetition code from quantum error correction. It then also finds there is a way to employ measurements, but just by being more smart. So setting aside one of the 4 qubits as what we would call an ancilla qubit, and doing controlled knots with this ancilla qubits, and then measuring the ancilla qubit. So this is the measurement going on here, and applying these measurements periodically. So it becomes better and better over time. And once this works for one particular set of qubits, you can really apply it to anything. Yeah, you can do different topologies. For example, having qubits in a chain. Maybe all the qubits can be measured, maybe only one of them, maybe it's a different kind of connectivity. And then you can run the same reinforcement learning algorithm and discover strategies that are really fine-tuned for this particular connectivity. And you also see these red boxes here. These are situations where one of those measurements indicated that something is wrong, that an error has happened in one of the qubits. And then you need another sequence, which the computer has discovered, in order to figure out exactly which error has happened and how to correct it. Yeah? And so then you can plot, for example, the effective improvement in the coherence time for the different connectivities, if you like. And we also applied it to many other different scenarios that, for example, are distinct from the stabilizer code that is being discovered here. Okay, so that worked already quite fine. I'm skipping over many details here because I want to come also to the more recent stuff. I should not pretend that this worked out of the box. There were many extra ideas that we had to put in to actually make it work. But that's an example of looking into quantum error correction. And we are now pushing this to higher qubit numbers by putting in a little bit more physics knowledge. We have also applied reinforcement learning to state preparation and stabilization. I will later come up to the topic of optimizing whole quantum circuits. But there's another question that arises, namely how to apply this to experiments, right? So what I've shown you before is, of course, a simulation. How to apply this to experiments? And there are many interesting questions. For example, how do you train? In order to train in an experiment, you need to find a way to get the reward from actual experimental measurements. Yeah? And then, of course, also, if you think of something like quantum error correction, you need to be able to react very fast. You need to react faster than the coherence time of the qubit. And again, that's not so simple. So we teamed up with the team of Andreas Wallraff, I guess one of the leading teams in Europe for superconducting qubits. And in particular, the subgroup being led by Christopher Eichler, who then now is faculty at our place in Erlangen. And we asked, how can we apply reinforcement learning on a superconducting qubit system? So just to give you the context, there has been a few first steps in this direction of doing reinforcement learning for actual physics, quantum physics experiments. For example, there was a nice paper trying to design better gates that was applied to a cloud-based quantum computing platform. There was another paper from the Natalia Ares group for tuning up quantum dot devices. And then recently there was a paper out by the Devoré group for having a quantum error correction protocol for so-called bosonic codes and optimizing parts of it using reinforcement learning. But in all these settings, there was actually no real-time feedback with a neural network agent going on. And the challenge in that is, of course, that this real-time feedback has to occur within the coherence time of the qubit. So that is what is really difficult in this setting. So what we managed to do together with the experimentalists was to come up with a solution that is really fast enough. So in this case, it was a single superconducting qubit that was controlled by a neural network, and the neural network was now no longer sitting on a PC somewhere, but really on a field programmable gate array. So that's a chip, so to speak, that can be reprogrammed and can be very fast. And then it can take in measurements, whole noisy measurement traces, voltage versus time, and based on these measurements decide what to do next and send down a pulse to the qubit in order to produce a gate on the qubit. And the whole cycle time here was less than 1 microsecond, which needed really some careful engineering. So part of the engineering was more on the, say, experimental side, programming the FPGA by counting every nanosecond that is spent in some multiplication or addition while you go through your neural network. But part of it was also more on the conceptual side. So we introduced a new neural network architecture where we modified it in the following way. Usually a neural network is evaluated by feeding in signal into the input and then layer by layer by layer calculating what should be the output. Now what we did here is, while the measurement data is coming in, the first little few nanoseconds of the measurement data is being fed into the input layer, then the calculation happens while the next few nanoseconds are also coming in. So to speak, the evaluation and the reception of the incoming signal, they happen simultaneously. And by that, of course, there's a price to pay, namely the last pieces of measurement data will only be evaluated in the very last layer, so that reduces somehow the power of the neural network to do a calculation. But there's a big gain because basically you are not losing time. The only time you're adding on top of the measurement that would have to take place anyway is only the few nanoseconds needed for evaluating this very last layer, so about 50 nanoseconds. So that's the total latency we are adding. Everything else would be there anyway. And so that enabled us to do this less than 1 microsecond cycle. Now, once you have this in place, you can use it to solve various tasks, but since this is the first time ever that such a neural network real-time agent has been implemented, we picked relatively easy tasks. So we have a single qubit, and we just want to initialize it in a ground state, in the ground state. Because you know the thermal population is not 100% in the ground state, so you want to improve it. And one of the simple ways you could do it is to measure the qubit, and if it's in the ground state, you leave it. If it's in the excited state, you flip it, and then you are done. But of course, maybe the flip is not perfect, maybe the measurement is not perfect, so maybe you want to do this multiple times. And so there immediately emerges the possibility to figure out a smarter strategy. And so then we gave this task to the neural network agent and reinforcement learning. And then once this works, you can also apply it to slightly more complicated situations. Here, for example, taking into account that the qubit also has a second excited state in which the qubit might find itself in after a complicated computation due to some leakage. Once you have trained this, you can start to analyze the strategy. And I should mention, this training in total in real time takes about 3 minutes. So you go through thousands of trajectories, always updating. So after each 1,000 trajectories or so, we send the collected data to a PC. The PC applies the reinforcement learning algorithm. It will be sent back down to the FPGA, and the parameters of the neural network will be updated. So once you go through thousands of those and have spent 3 minutes, the whole training has concluded, and you have a neural network implemented on an FPGA that is able to very efficiently initialize your qubit in the ground state. And then you can analyze the strategy. For example, you can ask yourself, what's the suggested action based on the observation? Now, in our case, the observation is this full noisy measurement trace, which consists of I don't know how many data points. So in principle, I cannot plot anything in this super high dimensional space, but I can, say, take the average and take another collective integral that characterizes my noisy measurement trace, and then I have a two-dimensional space in which I can plot the suggested action. So here these colors indicate different actions. So for example, here this orange blob indicates where the neural network suggests to take a pulse that would take you from the second excited state down to the ground state. So if it finds the measurement values are somewhere in this regime, that's the suggested action. And you can analyze all the other actions, and you can find that this totally makes sense. And this is all done on the real experimental device. So if you take the next device, which maybe has slightly distorted parameters, it would come up with a different strategy. So that's very promising. And of course, we're talking with them about applying this to multiple qubits, for example. Okay, so that is an important step to go towards experiments. Now I want to come back a little bit to things that are being done in simulation. And you recognized maybe in the first example that I gave you that the number of qubits was relatively low, 4 or 5. And one of the reasons was that you need to simulate things on the computer. So you have this exponential explosion of the Hilbert space if you go to more qubits, and then the simulations take more time, and we have to go through these simulations not only once or twice, but really thousands of times. So it really matters. The question then comes up, okay, but now if you do have 50 qubits or so, like in a NISQ device, these noisy intermediate scale quantum devices that people are now really building, what can you do? You don't want to simulate that on a classical computer, obviously. So one way would be to really do everything on the experiment. So that's one thing. But here we found another way. And we found it in a particular scenario. Namely, let's assume you have a quantum circuit that you produced out of a quantum algorithm, compiled it for this particular platform, so it does what you want it to do, ideally. However, maybe it's not very efficient. Maybe the gate count is too large or the depth is too large. And you're interested in shrinking this circuit, also to become more resilient against noise. Now, there's a smart way of shrinking such a circuit. Namely, there's a set of transformation rules. So, for example, if you discover there are these 4 controlled nodes next to each other, you can actually replace them by only 2 controlled nodes. And there's a couple of such transformation rules depending on the gate set. Now, the idea here will be, if you apply any of these transformation rules, the circuit still does exactly the same thing as before. So you don't need to simulate it to check whether it still does the right thing. It is an exact transformation. And so the idea arose that we would train, by reinforcement learning, an agent to discover where to apply these transformation rules. And so the loop is then the following. The environment, in the sense of reinforcement learning, would be a picture, so to speak, of the whole quantum circuit as it exists now. It would be fed into the agent. I'll tell you how in a moment. And then the agent has to suggest where exactly to apply a circuit transformation. And after this has been trained, this agent will become a kind of meta agent. It's an optimizer that will work for any particular quantum circuit that you give it. Okay, so a few words about how this works in practice. For example, how is the input encoded is a natural question in this kind of setting. The quantum circuit itself already looks like a 2-dimensional picture, so qubit number and time are the 2 axes. And then for each location in space-time, you have which gate is being applied, and that can be encoded in a 3rd dimension that is like color channels of a picture. And if the value is big in one of these slots, then that means, oh, this gate is applied at this location. So that's the input that is being fed into the neural network that represents the agent. And since it's this kind of 2-dimensional picture, we can use so-called convolutional neural networks, which are exactly the networks that people use for image recognition and which are easily able to scale up to larger images. So that is important. And then the output looks roughly similar. So again, it's like a 2-dimensional image with different channels, and the different channels now have the meaning of which transformation rule do you suggest to apply. And again, so the values that are being spit out here will represent the suggested probability of applying this particular transformation rule at this location in the circuit. Okay, and then when we train, we actually train in a random circuit. So we make a random quantum circuit, we blow it up, we shrink it again, and so on, and we feed this as tasks to the neural network agent, which then over time will become better and better at optimizing these circuits. And so here's an example of what comes out in the end after you've trained such an agent. What we applied it to here was really a 50-qubit setting, where the grayish part in the background would be the original quantum circuit, and the bluish part represents the quantum circuit after having been shrunk by the agent. And just to give you a sense of the timescales involved, we compared it against one general optimization technique, which is simulated annealing. So basically you apply a transformation rule. If it shrinks the circuit, you keep it. If it doesn't shrink the circuit, maybe you keep it stochastically still. And then applying it to this particular circuit down to some level of success requires about a week of running the simulated annealing. And that is comparable to the full training time for the reinforcement learning agent, which is also about a week. But now this reinforcement learning agent, after having been trained, can immediately be applied to any particular quantum circuit. And it doesn't need a week for that, but just a few hours. Of course, these numbers depend very much on the fine print and the settings and so on, but this is what is possible. Okay, so unless there are any questions, I move to the last part of the talk, but maybe there is some question here. Yeah. Yeah, so it's perfectly true. there is no way to do a complexity analysis. Now here, so for example, it would be impossible for us to predict in advance how long the training time is for a given measure of success. But once you have trained it, one thing we do know is that this was trained, for example, on a 10-qubit scenario, and yet we can very successfully apply it to a 50-qubit scenario. And the reason is that we're using these convolutional neural networks that are good for image recognition. And that only scales linearly. So if instead of 10, I use 50, the neural network application will just take 5 times more time. So that is relatively decent. Yeah, in the experiment. Yeah. So you mean not the experiment, but the original example, yes? Yeah, so in this example that I showed you, this was only a code that is, say, similar to the repetition code for either guarding against phase noise or against bit flip noise, and the 4 qubits were needed because I need one ancilla qubit. And now what we're doing these days, but I don't have slides yet here, is go to much larger numbers, and then of course we can do the full quantum error correction for arbitrary noise. Okay. Good. So there's another question.
Yeah, so in such circuits where there are large number of qubits involved, can an RL algorithm in principle discover new transformation rules whilst doing it, and at the same time maybe apply it as it goes along? Or are the transformation rules hard-coded and fed into the system?
Okay, yeah, very good question. So here they are hard-coded. We just have a handful of transformation rules. We spoke once about also discovering the transformation rules, but that would be, so to speak, a somewhat separate task. There we would then always concentrate on these rather small numbers of gates and numbers of qubits, and then we really have to simulate them, but this is okay for these small numbers, and check, oh yeah, you see, this is a new transformation rule. Yeah. There's also something else connected to that. Here you see these are more or less discrete gates, and that's nice to have these transformation rules. If you had, say, parametrized gates, say rotations by arbitrary angles, then typically it becomes a little bit harder. You don't have that many transformation rules, but it would be equally interesting then to discover some.
Just 2 quick questions. One is, this is essentially like Go, right? Because the whole point here is that the transformation rules are local in space.
Yeah.
And hence the 10 works on a 50 essentially because there's nothing too non-local happening. Exactly. So I just wanted to confirm. Yeah.
No, that's absolutely true. Yes.
And the other intuition that I have, which I just wanted to check with you, is that discovering new rules involves basically analysis at the Lie algebra level, and usually that is exponential, and so that's where the bottleneck is, right?
Yes, yeah. So here we don't do it, and we were happy with a handful of rules that we do apply.
Yeah.
But yes, and there we would have to remain at very small qubit, but it's still good because in the same spirit as here, we would then apply them to the larger setting.
In principle, you could do a block optimization with, let's say, less than 20 qubits. You could just go through a machine learning which would just do it, but then now you have new rules that you could deploy. Yes, 20 qubits at a time, which maybe...
Yes, yeah. Maybe 20 is ambitious, but
20
yes,
something,
yeah. Okay, yes.
Other questions?
There's another.
Or is the data also involves a quantum measurement?
So everything I'm doing here is classical machine learning.
Okay.
If I apply it to an experiment, of course, a quantum measurement will be involved.
Okay.
But other than that, there is, so to speak, if that's your question, no particular quantum machine learning component to it. So we are interested in applying it, so to speak, right now.
Right. So you're working with sort of analytical formula behind the scenes?
So to speak, yeah, but mostly it's numerics, of course. Okay. I mean, the underlying formulas for the algorithm are analytical.
You're not doing an actual measurement and getting a random outcome. That's not the sample, right?
Well, so for example, the strategies that are being discovered, like in the first example I showed, are of course strategies that deal with the random outcomes of quantum measurements as part of the strategy. But the reinforcement learning algorithm itself is a purely classical reinforcement learning algorithm and not something that in itself also has yet another quantum speedup, for example.
Okay. Got it.
Okay, good. Good.
So when you were talking about collaborating with the experiments for initialization to the ground state by choosing the appropriate operation.
Mm-hmm.
So in that model, does the learning strategy or is the learning strategy aware of the system parameters, or is it a black box strategy that?
It is really a black box strategy. Of course, if the system parameters were completely off, then none of these pulses would work, and even this reinforcement learning agent would not discover a good strategy. So the experimentalists make sure to calibrate these parts. But if they were a little bit off and then always lead to some extra leakage that you ideally wouldn't have, that agent would discover probably some way to fight against this. Okay, so maybe I move on. So now I come back to what I told you in the beginning. I said there is model-free and model-based reinforcement learning. Everything I talked about so far is really model-free in the sense that we are using algorithms that pretend they don't know the environment. They don't know what is going on. All they learn about the environment is really only by the interaction, because you observe, you act, you see how the environment changes. So implicitly, they learn a little bit, but not very much. Now, however, of course, in quantum devices, which we have well characterized, we often do have a model, and we are exploiting this in many settings. And the model we have is, of course, at heart, the Schrödinger equation to describe the quantum dynamics using parameters that hopefully our experimental friends have very well calibrated. So the question is, can we exploit this? And the general concept is we should be able to exploit this because, as I just told you, for model-free, there needs to be this implicit learning of what's going on, whereas for model-based, we already have a lot of knowledge, so that should make things more efficient. So model-based reinforcement learning. Now, the angle I want to take here is coming from another direction, namely quantum optimal control. Yeah? So forget about machine learning for a moment. Start with quantum optimal control, which has been ongoing since, let's say, the 90s or so, depending on where you start. For example, people discovering good laser pulses in order to split apart a molecule, or discovering good microwave and radio frequency pulses to do manipulations of spin systems, or now of quantum computing devices. Now, the general setting for this would be to say I have a controllable Hamiltonian that contains a few time-dependent parameters that I can change. So, for example, microwave amplitudes or magnetic field amplitudes that can change as a function of time. And it will be my task to find the optimal pulse shape so as to optimize some reward. So here again, I'm using the language that I used before. And the reward in the simplest cases could just be the state fidelity, so the overlap between the actual final state and some target state, if I want to do state preparation. Now, the most well-known generic numerical technique to achieve this goal is probably GRAPE, gradient ascent pulse engineering. This is one of the important papers in this field, introducing the technique, especially to spin systems and qubit systems. And the idea is rather simple. So you formulate your reward, and then you do direct gradient ascent. So you take the gradient of the reward with respect to the control field amplitudes. And you do it in a slightly smart way to calculate the gradient efficiently. But essentially, you're exploiting the fact that you know how your evolution does depend on the parameters, because essentially you're solving the Schrödinger equation. So this is the most generic numerical technique being used today for quantum optimal control. It's really the state of the art in modern quantum devices. And here's just one example from the Yale group, preparing a particular Fock state inside a cavity by sending in microwave pulses, which you can see here in yellow and in blue. And these have been optimized using GRAPE. You can already see one challenge is here the interpretability. So it's basically spaghetti pulses, and maybe the next time you run the algorithm, you get different results. Okay, so what's missing? Well, what I told you so far is really having a controller that has stored this pulse shape. It sends the pulse down to the system, and then hopefully the system ends up in the correct state. But what if there is noise? What if there is some bath to which the system couples? In that case, it would be good to remove all the extra entropy that this bath generates. And removing entropy here, that would be a case for feedback, just like I explained before. So you would like to have a detector that detects at least some aspects of the system, and based on those detection results, you apply certain controls. So conditioned on the detection results, you apply controls. That's feedback. Now, that's very important because it removes entropy and is important for many tasks like cooling or state preparation against noise, or quantum error correction, and so on. The challenge is, though, that if you wanted to apply something like GRAPE, figuring out these pulse sequences, while at the same time measuring and conditioning the pulses on the measurement results, there is so far no straightforward extension of GRAPE or other such gradient-based methods to quantum feedback. And the reason for that is simple. Namely, if you think about the quantum measurements that are going on, maybe you have strong projective measurements, if you like, so they have binary outcomes in the worst case. And then at least it's not obvious in the beginning how to do a gradient through these binary outcomes. So we set ourselves the task of combining this direct gradient-based control with feedback on the strong measurements. And our motivation was really that we had seen in one example that even if I don't do the feedback and just try to optimize pulse shapes, that something model-based like GRAPE worked much, much better for us than the model-free approaches that I've been talking about before. So it was much more efficient. So then we wanted to extend this also to include feedback. So the picture you could have is that in your Hilbert space, you have periods of continuous evolution where it's easy to take gradients. You just follow the prescription of GRAPE. And then once in a while, you do these jumps because you have a measurement, and depending on the outcome, you jump in Hilbert space. Here's another way of representing the same. So time runs to the right. And these yellow areas are the periods of differentiable evolution, which can depend on some control amplitudes, let's call them f. But whenever a measurement happens, your tree splits according to which measurement result was realized. And then these controls, they should depend in general on all the previous sequence of measurement results that you have acquired in order to implement feedback. So that's the challenge, to discover such feedback control strategies. So F depends on the sequence of measurements. And now how to do that? Well, we take a step back and we say our overall goal was just we have this reward and we want to optimize it and maybe doing gradient ascent. Now, in this particular situation, for each particular measurement sequence, there will be one reward, and for another measurement sequence, I come out with a different quantum state and the reward will be different. So what I want to optimize, presumably, is the average of the reward over all possible measurement sequence outcomes. And if I now take the gradient of that with respect to the parameters that enter my feedback strategy, I find that I need to be careful because the reward averaged over measurement outcomes contains two pieces. First is the reward for a particular measurement outcome, and second is the probability of this particular outcome. And both do depend on the parameters inside my feedback strategy, because the reward itself, well, that's the fidelity, let's say, the overlap with the target state. Of course, it depends on the full unitary time evolution, including these parameters of my feedback strategy. But also these probabilities for certain outcomes, that's just psi squared, Born's rule, and psi itself depended on the feedback strategy parameters. So both depend on these parameters. So if I now take my gradient, I obviously need to take the gradient of both parts. And then I want to rewrite things a little bit. So that's the first part, where I just got the gradient of the reward for a particular measurement outcome, and then I average over outcomes. And then there's a second part that at first looks different. You just have the gradient of the probability. But then you want to rewrite it in a way that allows you to do Monte Carlo sampling again over all possible outcomes. And so I stick in 1 divided by the probability and multiply that by the probability. And what you get then in the end is such a gradient of a logarithm of a probability. Okay. And so you need both of them to be correct. And the funny thing is, on the mathematical side, this is quite related to what also goes on in these policy gradient model-free reinforcement learning techniques that I showed in the beginning. But there's a distinction here, because there it was probabilities of discrete actions of the agent, so the policy, whereas here the probabilities that we're taking the gradient of are really the probabilities of measurement sequences, so they belong to the environment, the quantum device, they belong to the observations of the environment state. Okay, so that's already in a nutshell what goes on in this technique that we like to call feedback grape. I don't talk here about the technical details of how we implement the feedback control strategy. You could, for example, take a neural network. So this f of m1, m2, and so on, that could be a neural network where you feed in the measurement sequence. So this is one thing we tried. If you only have a few measurements, you could also simply write down a lookup table, all the combinations that may be necessary for all the possible measurement sequences. But in any case, we wanted to apply it to a few example tasks that are relevant for modern quantum devices. And one of the most prototypical devices that people look at in cavity quantum electrodynamics is having a cavity coupled to a single atom or to a single qubit. So that's the Jaynes-Cummings model here, this red atom coupled to a cavity. But now, in order to make it more interesting and include some feedback, we imagine that on top of that, we have another ancilla qubit, you could call it, also being coupled to the cavity, so that we always can learn at least a little bit about the state of the cavity. And so this ancilla qubit is coupled in a dispersive manner, so the number of photons, A dagger A, inside the cavity shifts the frequency of this particular qubit. And other than that, the controls we can apply is applying a drive to this qubit and also switching on and off the coupling between the qubit and the cavity. That is a very well-known set of control elements, and it has been shown, and that's important in this context, that leaving aside the feedback, these two elements, qubit drive and qubit cavity coupling, they are enough to prepare arbitrary quantum states inside the cavity. So that's a work from the 90s, Law and Eberly. So we are set to go and in principle do arbitrary things in this setting. And now here, just something about the measurement. We have this dispersive coupling, which just means that the ancilla qubit will precess at a frequency that is proportional to the number of photons inside the cavity. And therefore, if I then measure the ancilla qubits afterwards, I can figure out a little bit, at least, about the number of photons being currently stored inside the cavity. And that's not something wild we invented, but this is something that was actually done in a slightly different setting in the group of Serge Haroche for atoms coupled to microwave cavities. Okay. And so then we can set up our whole feedback control sequence. And instead of trying to figure out continuous pulses, we like to write things down in terms of parametrized quantum circuits because it's better to interpret. And so we imagine we have a measurement whose parameters we can control, like the interaction time and so on. And then we have these unitary controls like the drive on the qubit and the qubit cavity coupling. And so now you can go through various tasks, and these are the last slides I want to show. For example, even without doing any of the unitary controls, you can say my task is to purify a state. You start with a thermal state in the cavity, and you say I measure, which means you learn more and more. So you purify your state, you go to a pure state. But it turns out that if you choose your measurements based on previous measurement results, so in other words, if you do an adaptive measurement strategy, then you can purify faster because you can learn faster. You do the next measurement that gives you the most information. And that's shown here, and feedback grape discovers this. The next task would be state preparation from a thermal state. So what happens here is that you both purify the state by measurements and also prepare by unitary controls the desired final target state. And then the last task would be state stabilization. So here we gave the task of stabilizing my cavity in Fock state number 5, let's say. And if there is some decay event taking me down one level, then the agent has learned how to counteract this, and it does something wild, but after some time, it's back again in Fox state number 5. And the nice thing about this is, if our agent or if our control strategy is implemented using a so-called recurrent neural network, which is a neural network with memory, then we can train it on relatively short sequences, which is efficient, but the strategy then easily extends to arbitrary time, so it knows what to do forever, so to speak, to stabilize the state. And by now we have gone through several other tasks as well. So I hope I showed you that reinforcement learning is really quite a powerful technique that can be applied in a variety of different settings, and by now there's even first applications to experiments, which we find exciting. Okay, thank you very much.
Questions? More questions? Yeah, please.
Thank you for the talk. I can see this figure where you are, I think, injecting signal to various qubits, this circuit diagram, the one in the middle.
This one?
This one.
Okay.
And you mentioned that you are controlling the state of the qubit by introducing signals to this. Could you give an idea what kind of signals are there? What is the frequency?
Okay. So these are simply the normal microwave pulses at gigahertz frequencies. And these pulses, we do not, in this case, we do not optimize the shape of the pulses. So these are pulses that the experimentalists have pre-calibrated. They know the transition frequency. They know which pulse amplitude to send down for 10 nanoseconds or something like this. And then that pulse, for example, one of the pulses will flip you from the ground state to the first excited state, or between the second excited level and the ground state, and so on. So this is a small set of discrete, pre-calibrated pulses, and the agent is only allowed to say, I want this pulse, or I want that pulse. So it does not optimize the precise details of the pulse, which would be another task.
And by training them, you control the coherence between the qubits.
So in this experimental task, we had only a single qubit, and our only goal was to initialize it in the ground state. In the other tasks I showed before, of course, but they were done in simulations, we really wanted to preserve the quantum coherence across multiple qubits. And of course, it would be great then to show this also now in experiments, but we are still one step away from that.
Thank you.
Hi. So in supervised learning, right, we've fixed the model, which includes, for example, the number of layers, the number of neurons, and then often it comes down to the quality of the training data. So if I'm doing state estimation, I would say, what's the expressibility of data? Is there an equivalent of that in reinforcement learning to assess how my model would work?
Yeah, so the question is, are we limited, so to speak, by the expressibility of the neural network? So at the moment, there's always a little bit heuristics going in, and say we have a couple of layers, like 5 layers or 10 layers, and each of these layers maybe has 100 neurons or something like this. There was not an occasion where this was a very critical part. So we start with something like this and maybe slightly optimize it, but then we're happy about it. So that's not the bottleneck. What is much more critical in our experience is how we write down the reward, because there's actually many choices. You have a given task, but there are many choices for the reward function that encode this task, which become optimal when this task really is achieved successfully. And there's many choices. For example, even if you say, I just want to have state preparation and my reward should be the fidelity, you say, but you could take the square root of the fidelity or the fidelity raised to some other power, and this actually has an influence on how easy the training goes. And also, I didn't talk about it, but in the very first example, with quantum error correction, you could say my reward is based on what's the overlap of the final state with the initial state, because I want to preserve it. But this is a very sparse reward in the sense you have to go through the whole sequence, and then hopefully there's still something left from the initial state. So what we invented was a much better reward that already can query the system at intermediate times, how much is still there of the initial quantum information. And that turned out to be crucial. So yeah, so there is network architecture, but as long as the network is not super tiny, it's probably good enough. And then there's the reward engineering.
It's a very basic question. So I just wanted to distinguish the supervised learning and reinforcement.
Yeah.
So here in the reinforcement learning, we are providing the reward. So don't you think that it will work as a teaching? So let's say a student is there and teacher is what is doing after giving the exam, he is keep grading him and telling that you get the 0 or 100. So don't you think it will work as a teaching? So
yes. Okay. Yes. So let me say it like this. You could phrase every supervised learning task also as a reinforcement learning task by just giving rewards very immediately after each step. So the student does something, one step, gives an answer, so to speak, and then immediately gets a reward based on whether the answer was correct or not. What happens in more general reinforcement learning is the student does several steps without being told anything, and only if after the final step some goal has been achieved, you get a reward or not, which just makes it more complicated, as you can imagine. If someone guides you in every step, that's easier than if someone only gives you a reward at the very end if you did things correctly. But yes, every supervised learning problem can be phrased as a very simple reinforcement learning problem. Yeah, just depends on how quickly you get the reward, whether it's time delayed or whether it's immediate.
Yeah, so regarding the reinforcement learning that you talked about initially, so when you're talking about optimizing a strategy, you start with some random strategy and then continuously change a parameter, right?
Yes.
So how does this ensure that we would eventually end up with an optimal or converge to an optimal strategy? It could happen that there exist strategies which might be completely different, let's say, that might not be reachable by a continuous tuning of some parameter, right?
Yeah, so as long as our neural network is powerful enough, we believe that, so to speak, every strategy can be encoded. But you are right insofar as it could be that we get stuck in some local optimum. And this is really something that we also observed in our first test case. If we did not have this careful reward engineering and so on, we could easily get stuck in strategies which are far from the global optimum, but which are very hard to improve on locally. And so this really happens, yeah. And okay, either you engineer your reward, you introduce some noise, or maybe you just try it multiple times from different starting points. So there's no magic solution to that.
You talked about your neural network architecture. Can you talk about again, like putting the data at different layers? How does that help exactly?
So you mean this experimental part. So what happens here is we know physically that we have to spend some time on the data acquisition anyway. So what's going on here in terms of real time is several hundred nanoseconds of a noisy signal coming in. Yeah? And instead of acquiring them and then at the end sending them all to a neural network, which then has to be evaluated layer by layer and adding another few hundred nanoseconds, rather we are taking the first bits and pieces of the measurement data as they are arriving, feeding them into the input, then calculating the neuron values in the next layer based on that, and then feeding additionally the next few nanoseconds into this layer as well. So as we are evaluating the network, simultaneously the data is coming in, so we don't spend the few hundred nanoseconds twice. That's the idea.
Okay, I just have one quick question. Yeah. So there are open system grape algorithms that have that are around actually.
Yes.
We wrote one several years ago. So have you benchmarked against those? Like, because if you want to do a cooling task against or kind of defeat an environment, then one way to do it is. I imagine that feedback goes faster, but this is maybe.
Okay. So benchmark in the sense of comparing different strategies. Yeah. I guess we haven't done it. I guess this could be done, but then you need to think very closely about the experimental scenario that you're thinking of, right? Because how long does a measurement take? How strong is the coupling to the bath? That will determine which one is the better one in a given situation, I would say.
Sure.
Yeah.
Okay. I talk about this with you.
Yes.
But if there are no more questions, let's thank Professor Marquardt for this wonderful talk.